Okay, let's try to solve the try to come up with the answers for the question number 1 to 8 in your workbook 2. Right, right. The first question. It is a kind of a first statement, second statement question. Right. Let's come up with the question number 1. Right. Question number 1. First statement, second statement kind of a question. What it says. See, first statement says the shape of the electron density distribution of the 1s orbital of the hydrogen atom is spherical. The shape of the electron density distribution of the 1s orbital of the hydrogen atom is spherical. Yes, we know we have 4 types of orbitals. Right, this is about the first statement. We have with 4 types of atomic orbitals. Right, these orbitals. Right, basically that is spherical shaped, and we have p orbitals which are dumbbell in shape. Right, then we have d orbitals, right, actually which are double dumbbell. Then we have complex shaped f orbitals. Complex shaped. Right, so when it comes to s orbitals, yes, those are spherical in shape. So the first statement is true, as it is saying that the shape of the electron density distribution of the first 1s orbital of the hydrogen atom is spherical. Yes, the statement is true. The statement is true. What about the second statement? Let's come up with the second statement. Right, second statement, sorry. It says, according to the Bohr's theory, the electron in the hydrogen atom moves in a circular path. According to Bohr's theory, the electron in the hydrogen atom moves in a circular path. Right, when it comes to Bohr's theory, right, the electrons are moving in orbits. Electrons are moving in orbits like this. Right, electrons are moving in orbits. So it is kind of a circular pathway around the nucleus. That is our Bohr's theorem. So these are electrons, right, which are moving in orbits. Right, these are called as orbits. Right, circular pathway is there. So if you discuss more about this theory, Bohr ultimately said that the electrostatic attraction of these electrons will be equal to the centrifugal force, which is actually outward from the nucleus. That is how the electron becomes stable in this kind of a circular pathway without falling into the nucleus. That is what the Bohr's theory is, right? So F1 is equal to F2. The electrostatic attraction among the opposite charges, right? The electrostatic attraction is equal to centrifugal force, right? So this is the Bohr's theory. Yes, according to that theory, Bohr's theory, right? The electrons are moving in orbits, means a kind of circular pathway around the nucleus, right? So the statement is true, right? Two statements are true. Two statements are true, but we have to come up with answer number 2. We have to come up with answer number 2. Why is that? Because the orbital concept comes in the new atomic model, the cloud model. Orbital concept comes in the cloud model, the quantum mechanical atomic model. But when it comes to orbits are with the Bohr's theory. Two different concepts of atomic theories, right? So both the statements are true, but the second one won't explain the first one. That means we have to come up with the answer number 1. The answer is answer number 1. As is the first statement, second statement condition, right? Two statements are true, but the second one won't explain the first one. That means answer number 1. Right now, that is all about the discussion of the first question, first MCQ, right? Let's discuss the second MCQ, MCQ number 2, under the orbitals and quantum numbers, right? See what it says. It's a 5-choice question. You have 5 choices there appearing. So you have to select the best one out of those 5 answers, 5 choices, right? Let's go to the question. It says the number of shells, sub-energy levels, orbitals, and the maximum number of electrons that could be present in the main energy level described by the principal quantum number n is equal to 3 are respectively, right? What are the things looking at, right? So number of shells, we are looking for number of shells, right? And then we are looking for orbitals and looking for the maximum number of electrons. Maximum number of electrons. In what? In n equals free. N equals free energy level. In n equals free energy level. So n equals 3. N equals 3 means we are dealing with the third main energy level, right? The n describes as there is the first quantum number, described as the main energy level the electron occupies. Main energy level where the electron occupies, right? So that means n equals 3 means you are with the third energy level. N equals 3 means you are with the third energy level. Third energy level. Right? When it comes to third energy level, right? They are looking for subshells, right? Subshells. When it comes to third energy level, right? You have 3 subshells. So it's like this, no? When the energy level, which is denoted by n, for the first energy level, the subshell is present. It's only the 1s. For second energy level, you have 1s and 2s and 2p. For the third energy level, you have 3s, 3p, and 3d. Those are the sub energy levels available. Those are the L values actually, right? For the first energy level, only one L value is available. For the second energy level, you have 2 L values. In the third energy level, you have 3 L values. The L equals -1, 0, and +1, like that, no? So in the third energy level, you are with 3 subshells. Right? Okay. So 3 subshells are there. So number of subshells is going to be 3. Okay. Orbitals. How many orbitals are available? Yes, when it comes to orbitals, right? In S subshell, you have only one orbital. In S subshell, you have only one orbital. In P subshells, you are with 3 orbitals. 3 ml values are available for L equals 1. In D subshells, you are with 5 orbitals. 5 ml values are available with L equals 2. So that is the idea, right? So this is actually L equals 2. So you have 5 ml values. The ml is possible is -2, -1, 0, +1, +2. The ml values are the ones which will gives you the orbitals, right? So as when the L is equal to 1, you have 3 ml values, right? So ml is equal to -1, 0, and +1. For the L is equal to 0, right? You have only 1 ml value. This is the ml equals 0, right? So altogether you have, right, 9 ml values. That means 9 orbitals are available. Right? So you have it 9 orbitals. Maximum number of electrons. One orbital can occupy maximum of 2 electrons. So 9 orbitals can occupy, right, 9 to 18 electrons. This is the maximum number of electrons possible with the third energy level. the 18. So all of these orbitals are able to come up with 2 electrons as maximum. 2, 4, 6, 8, 10, 12, 14, 16, 18. So 18 electrons are possible as the maximum number of electrons at the third energy level. So the answer is going to be 3, 9 and 18. 3, 9 and 18. That means your answer is answer number 2. Answer number 2. Answer is answer number 2. That is for the second question, second MCQ. Right now? Okay. Let's go to the third one then. Right. This is question number 3. Question number 3. What it says? It says the identity of an electron in an atom can be expressed using 4 quantum numbers. Right? N, L, Ml and Ms. Identify which set of numbers given below is not acceptable as a set of quantum numbers for an electron in an atom. For an electron in an atom. Right, not accepted. That is what they are asking. Right, basically you have 4 set of quantum numbers in L, Ml and Ms. One can say this is the barcode of the electron, which gives all the properties of your electron, right, for quantum numbers. So you have restrictions, Lamai. You have restrictions with all the quantum numbers, right? What are the restrictions? What are restrictions? Right, these quantum numbers can't get all the values available, right? So restrictions with n, what are the restrictions? N can have only the positive integers, only the countable numbers. You can't have the 0, only the countable numbers. 1, the integer numbers. 3, whole numbers, right? 4, like that. So n should have countable, right? Positive integers, integer numbers. You can't have half values with n. The principal energy levels, first energy level, second energy level, third level, like that. So there should be countable positive integer numbers, right? These are restrictions, right? When it comes to L can't have each and every value. The number of the values possible for L is restricted by the n value. So basically 0 to right, n minus 1. Those integer values can be taken by L, right? Integer values. So 0 to n minus 1. So if the n is 1, n minus 1 is 0. So 0 to 0, all the countable on all the positive values. So it is just 0. If the n is equal to 2, n minus 1 is basically 1. That means 0 and 1 are possible as L values. If the n is equal to 3, 3 minus 1 is 2. So 0 to 2, the numbers 0, 1, 2, like that. So if the n is equal to 4, right, n minus 1 is 3. So that 0, 3, 0, 1, 2, 3. 4 L values are possible. N is equal to 4, sorry. Right, next value. When it comes to ML, not all the values are possible for ML. What are the possible values for ML? ML can be taken from minus L to along with 0 to plus L, the integer values. The integer values from minus L to plus L. Those are the only values possible for ML. Actually, that is restricted by L. Whole values. You can't have half values with these quantum numbers in L and ML. But when it comes to MS, the two values are possible. Those are the plus half and the minus half. Only two values possible are the plus half or the minus half. The two spins. These values represent two available spins with the electron, clockwise or the anti-clockwise, right? So these are restrictions, right? These are the restrictions. So the quantum number set, right, should be okay with these restrictions if we are to take it as a accepted quantum number set. Let's go to one by one. Right, they are asking for the which set of numbers given below is not acceptable. They are asking us the quantum number set which is not acceptable according to these rules, right? Let's go to this, one by one. The first quantum number set, right? If you think of the first quantum number set, first choice, it is like 420 plus half, 420 plus half, 420 plus half. So if the n is equal to 4, n is equal to 4, you can take the L values, right? 4 minus 1 is 3, 0 to 3, 0, 1, 2, 3. Yes, that is okay. So if the n is equal to L is equal to 2, you can take the ML values as minus 2, plus 1, 0, that is available, plus 2, plus 1 and plus 2. Minus 2, minus 1, 0, plus 1 and plus 2. 0 is available, okay. So as M is, the plus half or the minus half, those guys are available, so plus half is acceptable. So first quantum number set is okay. Second set, right, that is 3, 1, 3, 1, minus 1 and plus half. What about this, right? When the n is equal to 1, n is equal to 3, for the L as L values, you can have 0, 1, 2, 0, 1, 2, so 1 is acceptable. So when the L is equal to 1, when the L is equal to 1, you can have minus 1 to plus 1 along with 0 as ML values. Minus 1, that is available, 0 plus 1. So as M is, the plus half and the minus half are okay, so plus half is there, so that is acceptable. So second quantum number set is also acceptable, right? Let's discuss about third one, right? The third quantum number set. Third set, what it says. Third set says 3, 2 minus 3, 3, 2 minus 3 and plus half. 3, 2 minus 3 and plus half, right? So as n, 3 is available, it's a non-zero positive integer, 3 is available. If the n is free, as L values, 0, 1, 2 are available. The L value can be 0 to n minus 1, n minus 1 is 2, that means 0, 1, 2 are available, so 2 is okay for L. When it comes to ML, the ML values available here is minus 2 to plus 2. It will be restricted by the L value, minus 2 to plus 2. The L values available, ML values available. So that minus 2, minus 1, 0, plus 1 and plus 2. So minus 3 is not available for L2. Minus 3 for ML is not available for ML for L is equal to 2. Minus 3 is not available as ML as a ML value for L is equal to 2, because that violate this restriction. So if the L is equal to 2, the available values are minus 2, minus 1, 0, plus 1 and plus 2. But minus 3 is there, that can't be as a ML value if your L value is 2, right? So there's the false quantum number set, right? So your answer is this, So your answer is answer number 3. It is violated with the third quantum number, ML value, right? The answer is number 3. For the number 4 and the number 5, the two quantum number sets are okay according to these rules, right? Okay, that is all about the discussion for the third question right now. Okay, right, let's discuss about the fourth question, the fourth MCQ, right? Question number 4. See what they are asking. The maximum number of electrons having quantum numbers n is equal to 3 and L is equal to 2 in an atom are, right? So your n value is 3, n value is 3, and L value is 2, L value is 2, L value is 2, right? L value is 2. What they are asking is maximum number of electrons. They are looking for maximum number of electrons, right? They are looking for maximum number of electrons. Maximum number of electrons with n is equal to 3 and L is equal to 2, right? So n is equal to 3 means you are dealing with third energy level, right? The n value, the first counter number, represents the energy level of the electron, right? So L is equal to means you are dealing with the d subshell. You know the idea, no? Right? L value and the subshell. You know the idea, right? L value and the subshell. So subshell and L value. So if you are with S subshell, L value is 0. P subshell, L value is 1. D subshell, L value is 2. F subshell, L value is 3. That is the connection of the L value with the subshell. So you are dealing with L equals 2. That means this is about the D subshell. You know, in D subshells, right, you have 5 orbitals. In S subshell, you have 1 orbital. In P subshell, you have 3 orbitals. In D subshells, you have 5 orbitals. So 5 orbitals means maximum number of electrons. 5 orbitals means maximum number of electrons. 5 into 2 electrons are possible as the maximum number of electrons in a 1 orbital. So 5 orbitals are there. So maximum number of electrons are going to be 10. So this is all about the 3D subshell. In 3D subshell, you can have maximum of 10 electrons. No? So one orbital can occupy 2 electrons, no? Like this. Antiparallel spins, right? So maximum number of electrons possible with the 3D subshell, because the third energy level D subshell is actually 10, right? D subshells contain D subshells are with 5 orbitals. S subshell is with only 1 orbital. P subshells are with 3 orbitals. D subshells are with 5 orbitals. F subshells are with 7 orbitals, like that. So when it comes to D subshells, you are with 5 orbitals. 1 orbital can have maximum of 2 electrons. So maximum number of electrons possible is actually 10 electrons. So the answer is answer number 5. Answer number 5. Right? So that is about the 4th MCQ, right, for today. Right. Let's come up with the next one. Right. Now we are up to the 5th MCQ. Right? This is about the 5th MCQ. See what it says. The sets of quantum numbers associated with the last 2 electrons of an atom in an element are these trivials, right? They are giving us the last 2 electrons. This is about the last 2 electrons. What are the 2 sets of quantum numbers? The last 2 electrons of that atom, 3, 0, 0 plus half. It is 1. And the other thing is 3, 0, 0 minus half. 3, 0, 0 plus half and 3, 0, 0 minus half. Okay. Right? So if they have given you a quantum number set, you should be able to read that thing properly. See what it says, right? So this is all about third energy level S subshell. This is all about 3S subshell. Right? This is about third energy level S subshell. So L value is equal to 0 means S subshell. N value is equal to 3 means third energy level. That is how the things appear. The first quantum number gives you the main energy level, the third energy level. Second quantum number gives you the subshell. So this is about the 3S subshell. This is also about the 3S subshell. So basically, this is kind of an atom, right? Where the 3S subshell is as its outermost subshell, right? its outermost subshell is 3s, right? So, and we have two electrons in it. You have two electrons in it, right? So let's come up with the atom. So let's take it as X. Let's take it as X as the atom. So this is what we need to find, right? So its configuration is going to be then 1s2, 2s2, 2p6, and 3s. This is the outermost subshell, and there you have two electrons. You have two electrons. Those are, they are saying that those are the last two electrons of that atom. So last two electrons of that atom resides in its outermost subshell, right? So that is the idea. So you have 1s to 2s to 2p6 and 3s to as its configuration. So you clearly see you are with now 2, 4, 10 and 12 electrons. You are with 12 electrons in your neutral atom. So its atomic number should be 12. 12 electrons in your neutral atom means your atomic number should be 12. So 12th atom. So 12th atom is what? Or the 12th element is what? It is the magnesium. This is magnesium. So that is how we are supposed to solve this question. Right? This is about the magnesium's last two electrons, which resides in the 3s orbital, which occupy the 3s orbital. Right now? So the answer is magnesium for the question number 5. So the answer we can take it as answer is going to be what? So that is the answer number 3. Answer number 3 for the question number 5. Right now? Okay? Right. Right. Now we are coming up to the question number 6. MCQ number 6. Right. See what they are saying at the MCQ number 6. Which quantum numbers are associated with the shape of an atomic orbital in an atom? Shape of an atomic orbital in an atom, right? So basically you have 4 set of quantum numbers for an atom: N, L, Ml and Ms, right? Ml and Ms. So let's discuss a bit about the physical information we can gather from these quantum numbers, right? Physical information. We can gather from the quantum numbers, right? So N gives us the size of the orbital. N gives us the size of the orbital. N gives us the size of the orbital. So if you need some example, you know, the 1s orbital will be like this, the 2s will be larger, 3s will be even larger. So you clearly see when the n value increases, the size increases. The size increases, right? So n, the physical idea of n is all about the size of the orbital. This is valid for p orbitals as well. Then the 2p orbital, the 3p orbital will be larger. Then the 3p orbital, the 4p orbital will be larger. When the n value is high, the size will be high. Size will be larger. That is the physical idea of n value, the principal quantum number. Then the physical idea of L value, the azimuthal quantum number, is actually shape of the orbital. Shape of the orbital. Shape of orbital. Shape of orbital. So you know, when the L is equal to 0, the shape is spherical. When the L is equal to 1, the shape is dumbbell. The shape is dumbbell. When the L is equal to 2, the shape is double dumbbell. So according to L value, the shapes will differ. When the L is equal to 3, complex shaped. Right? So L value gives us the shape of the orbital, gives us the idea about this shape of the orbital. Right? Let's discuss about the next quantum number, Ml. Ml. What it represents. Ml. Ml represents us the directionality of the orbital, the three-dimensional arrangement of the orbital. 3D arrangement of orbital. or number of number of ml values also indicates the number of orbitals available. Anyway, 3D arrangement of the orbital. So it's like this. So this could be the p orbital available in the z axis, pz orbital directionality. So you can have the right orbital available in the x axis as well, px orbital. See, as well as the orbital can be available through the y-axis as well, pz orbital, sorry, py orbital. So these values, these orbitals will be given by different ml values. It could be ml equals -1, this could be ml equals 0, and this could be ml equals +1. So different mLs gives you different orientations of your degenerate orbitals, different orientations of your degenerate orbitals, right? Gives us the different orientations of degenerate orbitals. You know about the degenerate orbitals, right? Degenerate orbitals are the ones with the same energy and the same shape, but differs only with the 3D arrangement. Differs only with the 3D arrangement, right? The orbitals with same energy as well as same shape, but differs only with the 3D arrangement. Those are referred to as degenerate orbitals, right? So those will be represented by the ml values. The physical idea is that it gives you the 3D arrangements, the ml values. And the final counter number is ms, right? ms, right? ms. That's that guy's physical idea. What is that? When it comes to ms, it gives you the rotation. It gives you the rotation of the electron, right? It could be anti-clockwise or clockwise, right? Rotation of electron could be clockwise, rotation on the spin, right? Clockwise or anti-clockwise. Right? So plus half and minus half. M is plus half. Okay, say it minus half and M is plus half. So that is about the ms values, right? Gives us the spin of the electrons. Those are the physical ideas about the contour numbers, right? And this question asks us about the shape of an atomic orbital. Shape of an atomic orbital. Shape is given by L value. Shape is given by L value. So the answer is 1. Answer is 1. Answer is 1. Answer is 1. Shape is given by L value. That's a means quantum number. Right now? That is all about the question number 6. Right? Right. Quickly go to the question number 7 as well. Right? Let's do the question number 7. Right? Right. The question number 7. See what it says. It is like this. The maximum number of electron pairs of an atom that are associated with the principal quantum number n is equal to 3. So principal quantum number n is equal to 3. That is what we are referring to. N is equal to 3 means we are dealing with the third energy level. Third energy level. Right? In a third range level, what are the subshells available? The subshells available are actually what? Subshells available are 3s, 3p, 3d. Those are the subshells available. With the n is equal to 3, these are the L values available. L is equal to 0, L is equal to 1, and then equals to 2. Right? 0 to n minus 1. Right? Okay, then what they are asking? They are asking maximum number of electron pairs of an atom associated with these things, right? So maximum electron pairs. So with the 3s, you are with only one orbital. With the 3p, you are with 3 orbitals, 3 ml values. With the 3d, you are with 5 orbitals. So to count the maximum number of electron pairs, you have to decide how many orbitals are with, right? So basically, in the third range level, you are with 9 orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9. So third range level contains 9 orbitals. 9 orbitals means 9 electron pairs. They are not asking for maximum number of electrons, they are asking for electron pairs. So 9 orbitals means, right, 9 electron pairs. Right? So electron pairs, no? So in orbitals you have paired electrons like this, electron pairs. So with 9 orbitals, you are going to have 9 electron pairs as the maximum, right? 9 electron pairs. So the answer is going to be answer number 5. Answer number 5. Answer number 5. Right now, that is about the question number 7. Right? Let's come to the question number 8. Question number 8. Let's discuss the question, right? The number of electrons in the manganese atom, which is the 25th one, that have quantum numbers L equals 0, Ml equals minus 1. Yeah, that idea is you are referring to manganese, the 25th atom. First, write the electron configuration of that thing. 1s2, 2s2, 2p6, 3s2, 3p6, 18 done, right? 4s2, 3d5, the 25th. Okay, it's done. And they are asking for that have quantum numbers L is equal to 0 and Ml is equal to minus 1. Right? L is equal to 0 means, L0 means this is about which orbitals? S orbitals. L0 means we are dealing with S orbitals. And Ml is equal to minus 1. Ml minus 1. Right, so have quantum numbers L is equal to 0 and Ml is equal to minus 1. Ml is equal to minus 1. That thing will be available with p orbitals, right, and d orbitals as well, right? So L is equal to minus 1 means, as you are with a restriction, Ml equals minus 1 is possible when L value is greater than or equal to 1. L value is greater than or equal to 1. Because when L value is equal to 1, you can have these Ml values, minus 1, 0, plus 1. When the L value is equal to 2, you can have minus 2 to plus 2 Ml values. So Ml is actually minus L to plus L, no? Along with 0. So they are also, right, minus 1 is possible as a Ml value for even the L is equal to 3, but that won't be available with the with your manganese. But anyway, if the L is equal to 3, still you can see a -1 appearing. See, so the L value -1, sorry, ml value -1 could be there if your L value is greater than or equal to 1. If the L is equal to 0, you won't have ml -1, right? So these are the possibilities, right? So actually, right, these are the ideas. So in your atom, the manganese, we should look for this as well as this, right? First of all, let's discuss about the L0 electrons. L0 electrons, right? L0 electrons. So I'll go with red color. I'll go with red color, the L0 electrons, right? L0 electrons, red color. So here you have two. Here you have two electrons in these orbitals. Here you have another two. Here also you have another two. Even fourth shell you have some two s electrons. So L0 electrons, right? The total number of L0 electrons is going to be 8. Total number of L0 electrons are going to be 8. The electrons appearing in the S subshells, appearing in S subshells, right? Okay. Then we are trying to come up with the ml -1 electrons, the ml -1 electrons here. So ml -1 will be appeared with p subshells. L equals 1 means p subshell. L is equal to 2 means d subshell. L equals 3 means f subshell. But f subshells are not there with the manganese, right? No need to consider this. So we need to come up with number of electrons at the p subshells as well as d subshells, right? So with those subshells, you are with ml -1 electrons, right? So with all the p subshells, you have only one ml -1 orbital, so that only 2 electrons are appearing there. With every p subshell, only 2 electrons are appearing, right? As a maximum. So even though you have 6 orbitals here, even though you have 6 orbitals there, I'll go with a different color for that, right? Even though you have, even though you have 3 orbitals here, only one orbital represents the ml -1. So there you have 2 electrons with ml -1, right? Here they have 2 electrons. So it's like this, no? So you have ml values -1, 0, +1, no? So with this, that is what we are referring to. You have only 2 electrons. With this one even contains ml -1, 0, +1, no? There also with the ml -1 you have only 2 electrons, right? Here also you have ml values -2, -1, 0, +1 and +2, no? With ml -1 you have only 1 electron here, because here, right, the shell is like this, no? According to Hund's rule, the 5 electrons are filled actually parallel to each other, no? For this most stable configuration. So you have only one there at the ml -1. If you have to put the ml values here, -2, -1, 0, +1 and +2, no? So only one electron there at the ml -1. So altogether, the number of ml -1 electrons are 2, 4 and 5. Number of ml -1 electrons are 5 actually, right? So 5. So the answer is going to be 8 and 5. 8 and 5 means that is your answer number 3. Your answer number 3. So answer is going to be number 3. Right now, that is about the 8th question. And that is all for today, right? We had just discussed all the MCQs appearing in your workbook under the content numbers and the orbitals, right? So this is the review. This is a short review about those questions, right? Then for today, we'll wind up at this stage, right? And with the next lesson, next day, another clip, right? I'll send you the reviews about the other questions appearing in the resource book. Sorry, appearing in the workbook. Right now, goodbye then.